received his M.Sc and B.Sc degree in chemical engineering in 2011 and 2007 from the University of Engineering and Technology, UET, Peshawar, Pakistan. He was awarded the University Gold Medal as an acknowledgement for his exceptional performance during his undergraduate studies. He also worked as a lecturer in the Department of Chemical Engineering, UET Peshawar, for a period of 5 years. Dr. Ihsan research interests are applications of novel material in water treatment and desalination, adsorption, and environmental engineering. He has published around 40 research papers in high-impact referred journals and presented his work in 13 international conferences. He also holds 3 US granted patents. His work has been cited over 1900 times with an H index of about 19. Recently, he has also been awarded the highly cited paper award from KFUPM. He is serving as the editorial board and reviewer board of various journals and has reviewed more than 110 papers for reputed journals. He has also worked as a team member who successfully completed more than 50 environmental impact assessments and environmental monitoring projects for various clients. I welcome you, sir, on this platform. Thank you so much for volunteering for a lecture today. Over to you, sir.
Okay, thank you, Arzu, for the nice introduction, and also thankful to UEM Power Pakistan for providing me this opportunity to interact with the young scholar. So today I have selected the topic, and I will talk mainly about two novel material. One is not very novel, but the second one is very novel, and I will briefly describe its application in water purification. But for this lecture, I will mainly focus on the research challenges and the research opportunity, and it will be good for the young scholar who are looking for MS topic or PhD topic. So you can work in this area and you can do some breakthrough research. So before starting my lecture, I will just talk a little about my university, King Fahd University of Petroleum and Mineral, or KFUPM. This is one of the oldest university in the kingdom, and it is famous for its global repute, both in education as well as in research. Some departments in KFUPM, they are ranked among the top 10 globally, like petroleum engineering, mineral and mining engineering. So it's basically engineering university. And the center where I'm working is basically the Center for Environment and Water. And we are mainly involved in the environmental impact assessment projects and monitoring projects for various clients whenever they initiate a big project. So our center is basically conducting the study how adversely it will impact the environment and how can we minimize these impacts. So my lecture will be divided into two parts. And the first part, I will mainly talk about the carbon nanotube, where I work a lot in this area. And as I mentioned, I will focus on the opportunity and challenges. And the second part will be this novel material Mxenes, where there is a lot of potential for the young researcher to work in this area and to do some breakthrough research. So what is basically the challenge if we talk about water treatment? You might have heard this terminology that water is the new oil, water is the blue gold, and the future wars will be on water, not on the oil. This is because we all know that 97% water available in the world is salty water and 3% water is fresh water. But very few of you might know that we don't have access to all this 3% of fresh water. Because even in this 3% of fresh water, some water is frozen, some it is underground, and some is available in the form of lakes and river. So if we see the availability of water, it is less than 1%, we can easily access, okay? And due to this situation, it is one of the prime goal of the United Nations. You might know that they have defined 17 sustainable development goal. And the goal number 6 is clean water and sanitation, which is the prime goal, just to provide access to safe drinking water globally. So what are basically the solutions? So we have the water, whatever we have, we cannot increase the resources. However, one way is to recycle and reuse the water, whatever we have. And I will share two successful story here. One is from the space, and of course, other one is from the Earth. You know about the International Space Station. So there is no water available, and the only option for the scientists working there is to recycle and reuse the water that is discharged from the toilet, and even sweet, and even from the atmospheric moisture. So it is basically a water recovery system, and they have successfully recycled the water, and annually around 6,000 water is basically recycled. So this is a successful experience in the space. Another experience is the Singapore new water system. What they are doing basically, they are collecting all the water from the sewage system, and they are converting it into potable water. Because Singapore don't have the water, they have some agreement with the Malaysia a long time ago. Now they have some issue. So they are basically recycling their wastewater. And currently, of course, they are using it for the industrial purposes. But their regulation or their claim is that it can be used and it is fit for drinking. Of course, there are some issue about the public awareness and the public acceptability about this water. But this is very important finding that the wastewater we have, it is also an asset, and we can convert into potable water, even it can be used for drinking purposes. So if we want to recycle water, we should know that what are basically the various impurities in water and what are the available techniques. So I have highlighted basically few of the impurities that are most commonly present in the wastewater, including metal, organics, microorganism. And currently various techniques are available basically to treat this water. Of course, all these techniques have their own limitation, and they have their own benefits as well. The second option is desalination, where we can treat or remove the salt from the water, from the seawater, and we can get basically the clean water. So the salt concentration in the seawater is 35,000 ppm. Usually we want to reduce it to less than 500 ppm to make it fit for the drinking. And there are various techniques available, thermal techniques, membrane techniques. But here today my topic is how this new technology, which is called nanotechnology, will help to improve these available techniques, or they can propose some novel techniques for water treatment as well as desalination. So this slide is for those people who don't have much idea about the nanomaterial or nanotechnology. So it just represents the size at nanoscale. And here you can see the size of various objects at nanoscale. Nano basically means 10 to the power minus 9. So just to give you the idea how small the nanometer scale is, if you see the thickness of a sheet of paper, it is around 100,000 nanometer thick. And similarly, if you see the human ear, it is around 80 to 100,000 nanometer wide. And similarly, nanometer is the scale, it is the length in which your fingernail goes in 1 second. So you can imagine this is very, very small scale. And the properties of material at this scale are very different, and you can get some very fantastic properties that are basically useful for various attractive applications. So if we talk about nanomaterial, of course, various nanomaterial are available. One big family is the carbon family. There are metal-based, there are some composite. And the carbon family, two important member are the graphene and carbon nanotubes. I will talk about carbon nanotubes in a while. The second class is the 2D nanomaterial. Of course, after the discovery of graphene in 2004, various 2D material came into the limelight. And I have highlighted here a few of them, which include the hexagonal boron nitride, metal organic frameworks, LDH, and Mxenes. So, of course, I will just focus today on these two material, carbon nanotubes and Mxene, and I will just discuss the its various application as well as the research opportunities. So again, this is some basic slide for those people who don't have the idea. This is graphite, and graphite consists of various layers, and a single layer is called graphene. It's a 2D material. And if we roll this single layer of graphene, so it can form a tube. So it can form a single wall tube if you roll a single layer of graphene, and if you roll multi-layer of graphene, it can form multi-wall carbon nanotube. So these carbon nanotubes have some very fantastic properties. Its strength is almost 30 times higher than steel. It has excellent electrical and thermal conductivity, as well as it has some other fascinating property for various applications. So, of course, I will talk today mainly about water treatment. Just to give you the idea how this graphene is produced, it cannot be produced, of course, by rolling the sheets. There are various techniques available for the production of carbon nanotubes. One of the technique is the chemical vapor deposition, which can be used to produce comparatively large amount of the CNTs or carbon nanotubes. So here we use basically a carbon source, and we heat it at high temperature. So decompose in the presence of catalyst, of course, this is very important. So decomposition occurs, and the carbon nanotubes is produced. Of course, there are various parameters that control this process, the choice of this precursor material, the flow rate, the choice of the catalyst, the temperature. I will not go in detail of those. Some key challenges here are, although the CVD can be produced for the can be used for the production of large amount of CNT, but still the production yield is very low. And similarly, it's very hard to control the properties of the carbon nanotubes produced at this technique. And also, we should work hard to produce the modified carbon nanotubes. So this is another challenge. So there are a lot of research gap in this area where a researcher can focus and they can do some breakthrough research. So how this carbon nanotube can be applied in water? So it can be applied as an adsorbent, and again, for those people who don't have the idea, so adsorption is the process where the material or various molecule or ions are deposited on a solid surface, and they are physically or chemically attached to the surface. So carbon nanotube can be used as an adsorbent for the uptake of various organic and inorganic molecules. And this is how it can be used as an adsorbent. This is a bundle of the carbon nanotubes. So remember that carbon nanotubes usually tend to agglomerate due to van der Waals forces, and they will be held together by these forces. And of course, this is one of the major challenge that we should develop some technique to properly disperse the carbon nanotube for various application. So these are various carbon nanotubes, and here this closed tube represent the metal catalyst is there. Because when they are coming from the CVD directly, so you need to remove the metal catalyst first. And these four are various sites where the different molecule can be adsorbed on the surface of these carbon nanotube. So it can be adsorbed inside the carbon nanotube itself if it is open. It can be adsorbed between the channel and the CNT on the external grooves and the external surfaces. And of course, I'm talking here about the non-functionalized or pure carbon nanotubes. If you functionalize or modify the surface of the carbon nanotubes, then of course the number of these adsorption sites can be enhanced. So our group KFUPM, we have worked extensively in this area, and we have published more than 100 papers specifically focusing on the application of carbon nanotube and water treatment as adsorbent, functionalized carbon nanotube, production of carbon nanotubes, and carbon nanotube-based composite for various applications, mainly environmental application. So beside the adsorption, another application is the application of CNT in the membrane. So it can be applied as a filler material in the membrane. So this is a polymeric membrane or mixed matrix membrane. So if you add the carbon nanotubes here, various studies demonstrated that after addition of the carbon nanotubes, the characteristics of this membrane is increased. We are normally getting the high flux, the hydrophilicity is increased, and the membrane gives high salt removal or antibacterial or anti-fouling characteristic. So in this case, the CNT is randomly dispersed in this polymeric membrane, while in this case, the carbon nanotube can be vertically aligned into the polymeric membrane. So of course, both of these have their own characteristic, and I will discuss both of these techniques in a little detail in the coming slides. So this is the polymeric membrane, which is modified by the addition of the carbon nanotubes, vertically aligned carbon nanotubes. So here you can see that these are the various channels for the flow of the water molecule through the this composite membrane. So the water molecule can flow beside the carbon nanotube due to hydrophobic effect. because this carbon nanotube, inherently it is hydrophobic. Of course, you can modify the surface and you can make it hydrophilic. And furthermore, the water molecule can flow through the space between the carbon nanotubes, and also it can flow through the interior of the carbon nanotube. But of course, in this case, you have to remove the catalyst so that this channel should be available for the flow of the water molecule. And also, of course, the water molecule can flow through the polymeric matrix itself. Here, the carbon nanotube, this is the same structure, but the carbon nanotubes are randomly dispersed. So in this case, we can expect comparatively less flow of water, because some of the channel, for example, the interior, the flow through interior of the CNT will not be available here. So the flux in this type of membrane, where the CNT are vertically aligned, is high as compared to the this orientation where the CNT are randomly distributed. So generally, the flux in this type of membrane will be 3 times higher than this type of the membrane. But if we talk about the pure polymeric membrane without the modification, then of course the flux in both these cases is extremely higher than the pure membrane. And what is the significance of this? If the flux is high, then of course you can clean more water in in a shorter time. Of course, you also need to focus on the removal efficiency as well. I will talk about that in the coming slide. So what are basically the advantages of adding the CNT? As I mentioned earlier, it increases the hydrophilicity, so you can expect high flux. It increases the thermal and mechanical stability that is required for some application. And also it improves the antibacterial and anti-fouling characteristic of the membrane, as well as the salt reduction efficiency. If you compare this with the commercial RO membrane, so the flux is almost 1.5 times higher than the commercial membrane. And this is a very big statement. Remember that the commercial RO membrane are currently dominating the water treatment as well as the water desalination market. So if you can provide some membrane that can provide the same flux or even higher, so this is really a breakthrough technology. Then, as I told earlier, the carbon nanotube can be modified or functionalized, and it is found that if you modify the surface of the CNT, so its properties are further enhanced, and they exhibit more fantastic properties compared to the pristine carbon nanotubes. So this is just one example. Here you can see that this line with the black color, it represents the flux through a membrane without the carbon nanotube. And you can see that water flux is very low. But if you add the amount of the carbon nanotube, here functionalized carbon nanotube is used, so the flux is increased. Okay. Also, if you see the flux recovery or the ratio of the final to initial flux, so in this case, what it represents basically, if the ratio of final initial flux is high, this means that the membrane had less fouling, and it can be used in long run without fouling. Okay, so this is very low in case of the membrane without the carbon nanotube. But if you add carbon nanotube, so this ratio is increased. This means that less fouling occurs. Of course, there are some other detail. I will not go at this stage. You need to modify the dosage of the carbon nanotubes. Okay, because if you add a large amount of the carbon nanotube, some agglomeration might occur. And due to this agglomeration, the properties will be reduced again. So you need to define that optimum dosage basically. Okay, so as I mentioned that I will talk mainly about the challenges and research opportunities, and this is especially for those young graduate or the fresh student who are looking for a topic for their MS study or PhD study. So these are the challenges in this area, and you can work on these challenges to address it. One is the aggregation of the carbon nanotubes. As I mentioned, we have worked a lot in this area, and we try to develop some technique to properly disperse the carbon nanotube, but still there is a lot of potential to develop some techniques who can avoid the aggregation of the carbon nanotube. So this is one area. You can develop some ways how can we avoid this aggregation, because aggregation will reduce the properties in various applications. Then if you are adding the carbon nanotube into the polymeric membrane, remember all this is happening at a nanometer level. So how can you control the thickness of the layer? Because again, you need to define an optimum layer thickness. If it is very low or if it is very thick, then of course the property will be disturbed. So this is another challenge. You might develop some modification techniques of the polymeric membrane where you can add CNT with the control thickness. Secondly, this is the carbon nanotube produced, and this is the catalyst. Okay, the carbon nanotube during production, especially in the CVD, it will grow on a specific catalyst, usually the iron-based catalyst. Now, for various applications, you need to remove this catalyst. So there are some ways to remove this catalyst, but of course, it will damage the properties of the carbon nanotube. For example, acid treatment is commonly used. But what is problem in the acid treatment? It will remove the catalyst, but it will reduce the length of the CNT, or sometimes it will break the CNT. So again, there is a potential in this area. You can develop some techniques to develop a most efficient way to remove this catalyst from the CNT. Then of course you need to select the proper material for the CNT where you can add CNT to improve its property. Similarly, if you want to modify the surface of the CNT, again, usually acid treatment is used. And I mentioned that acid treatment can, deform the CNT, or it can damage the CNT. So you need to develop some other technique to modify the surface of the CNT to enhance its properties. So these are some of the challenges in this area. If we talk about the desalination potential of this membrane, most of the work is done basically theoretically, and some of the simulation model show that the water flow through the interior core of the carbon nanotubes is extremely fast. And this is E1.324 order of the magnitude higher than predicted by the famous Huygens-Poiseuille equation. So this means that extremely high flux of water can be obtained. If we apply the same technique, so the water molecule can pass through the interior core of the carbon nanotube, and the salt molecule or various impurities can be rejected. So again, this is another breakthrough research if it come into reality, that you can clean more water or desalinate more water in a shorter time with improved efficiency. So after these theoretical prediction, some researchers tried to form the carbon nanotube membrane. Here, remember, we are talking mainly about the pure carbon nanotube or a standalone carbon nanotube membrane. So some researchers tried to develop some standalone carbon nanotube membrane. Here is the summary. One way is to develop the template-based open-ended CNT membrane. During production of the carbon nanotube through CVD, the carbon nanotube can be deposited in a specific template, okay? And then you can open the tips of the carbon nanotube, and it can be used basically for the flow of the various molecules or water molecule, and can reject basically the salt. So this is one way. Another way is that you can aggregate or vertically align the carbon nanotubes. And here the main force basically to hold the carbon nanotube together is van der Waals forces. But the problem with this type of membrane is basically the strength will be very low, because van der Waals forces are very weak, so it might not suitable for application in real desalination or water treatment. So to overcome this, some polymer can put basically in the spaces between the carbon nanotube. So they will hold the carbon nanotube together. But in this case, since you are putting the polymer in the spaces between the carbon nanotube, so those channels will not be available for the flow of the water molecule. So in this case, the tips of the carbon nanotube must be open, and these are the only channel available for the flow of the water molecule. Similarly, some researchers try to form a radically aligned carbon nanotube membrane, and this is basically an in-out structure where you can allow the wastewater, let's say, to flow through the membrane. So the water will come out, and of course the molecule or the impurity will not come out, and here you can get the filtered product. And the last one is the Bucky paper membrane. This is again a very simple structure, but the strength will be low. You will disperse the carbon nanotube in a specific solution, and then you will filter it. And once you get the filtrate, you can just make it dry, and a sheet will be formed, which is made entirely of the carbon nanotube. But of course, there is no force to hold the carbon nanotube together. So the strength of this type of membrane is also very low. So I will just discuss the desalination potential briefly, and then I will share some of our research experience, what we did basically to develop some novel class of this membrane. So if you imply the carbon into a membrane, so the ion can be separated by saving effect, or it will be a size-based separation, okay? If we compare the salt rejection with the commercial NF membrane, so they are similar. Again, this is a very big statement. If they can replace the commercial membrane, which is dominating basically the market nowadays, so it will be a breakthrough research. Again, if you use the ultra fine nanotubes with the inner diameter less than 1 nanometer, then you can get basically some very fantastic property, and some electrostatic interaction will also occur, and the salt removal will be increased. But I will discuss later that obtaining carbon nanotube with this less diameter is very difficult. So this is another challenge, okay? And these carbon nanotube membranes show low bifouling potential as compared to the commercial membrane. Of course, low energy requirement. Remember that desalination in most cases is the energy extensive process. So if you can offer some technology with less energy consumption, so it will be really amazing. Then if we discuss the carbon nanotube with various wall, so generally multi-wall carbon nanotube is very easy to prepare as compared to the single wall or double wall. But interestingly, the single wall and double wall nanotubes have more attractive or fantastic property as compared to the multi-wall carbon nanotube. So this is another challenge. If we can develop some techniques to produce specifically the single wall or double wall carbon nanotubes, so you can basically improve the characteristic of the existing membrane. So a quick overview of the comparison of the vertical aligned CNT membrane with the ultrafiltration membrane. So this is ultrafiltration membrane, this is vertical aligned CNT membrane, and clearly you can observe that the flux is extremely high as compared to the ultrafiltration membrane, okay? And if you compare this with the mixed matrix membrane, so of course in the vertical aligned CNT membrane, the flux is even higher in the mixed matrix membrane. But as I mentioned earlier, there are some challenges associated with the synthesis of these type of the membrane. If you talk about the salt rejection, it is same as the RO membrane, brackish water RO membrane, which is used currently in the desalination market. So this is again very attractive feature, and it has more anti-fouling potential as compared to the commercial ultrafiltration or the nanofiltration membrane. Currently, it is not employed in the industry. Again, this is another challenge. Someone can work hard to bring it into the commercial scale. So these are the possibility if it can be applied on the industrial scale. So what are the possible configuration of this type of the membrane? Okay, for the mixed matrix membrane, spiral wound seems attractive feature, and for the vertical aligned membrane, plate and frame can be employed. So these are the challenges which I somehow mentioned earlier, that the carbon nanotube should be uniform for application in desalination, and it is very difficult to produce the uniform carbon nanotubes. So this is one research area one can work. Similarly, for these application, the diameter of the carbon nanotube should be very small, less than 1 nanometer or 0.6 nanometer. The problem is with the current technology, we can get up to 1 to 2 nanometer. So again, this is an open research area. Someone should work to produce the CNT with less diameter. Similarly, the single wall carbon nanotube and double wall carbon nanotube, as I mentioned, they are more attractive. They have more fascinating properties, but their synthesis process is complicated as compared to the multi-wall carbon nanotubes. Okay, and similarly, if you want to grow the carbon nanotubes vertically, this is another challenge. There are various issues. So again, some technique can be developed to grow the carbon nanotubes in the vertical direction. Okay, some other application of the CNT-based membrane I will briefly highlight here. It can be employed in the Capacitor Deionization. This is a process where basically two electrodes are used and electric potential is applied, and the positive and negative ions, cations and anions are separated basically due to electrostatic interaction. The carbon nanotube has the potential to be used here, interestingly, both electrode as an anode as well as a cathode. Okay, so you can modify basically the surface to make it like negatively charged to attract the cations, and here you can modify the surface to make it positively charged to attract the anions. And since there are various adsorption sites, so it can replace the current material used for the CDI. By the way, various carbon based material are used, but CNT can be an ideal candidate in this area as well. Similarly, it can be applied in membrane distillation. So I will briefly explain membrane distillation as a process where basically we are not using any high temperature. Here the pressure difference can be used for the flow of the water molecule here. Okay, so the water vapor will pass to this membrane. Okay, we will heat, water vapor will be formed, it will pass here, and here it can be condensed. So clean water can be obtained here, and the impurities will remain on this side. So if we imply carbon nanotubes, what will happen? It will enhance the flow of these vapors or water molecules, and more water can be condensed here or can be produced here. So it also has the potential to be applied in the membrane distillation. Here I will share briefly our experience with the carbon nanotube membrane. We basically produce a novel class of the CNT membrane, different from what I mentioned earlier. What we did basically, we modified the surface of the carbon nanotube with various metal and metal oxide, for example, iron oxide, aluminum oxide, and silver. And then we employ these material in water treatment and batch experiment as adsorbent. And we found that if you modify the surface of the CNT, so you will get very attractive features. It improves the surface area, it improves the absorption capacity for various ions and even anions and some organic molecules. But what we did basically, we used this material, this modified carbon nanotube, to produce a membrane entirely made of the carbon nanotubes. So this is just TM images of the carbon nanotube modified with various loading of the iron oxide. So you can see here that iron oxide is attached to the surface of the carbon nanotube at low loading. Similarly, at higher loading, some agglomeration of the particle is visible. At 10%, we are getting somehow the optimum dosage. So the particle are attached to the surface uniformly. So what we did basically, first we modify the surface of the carbon nanotube. Okay, there is a procedure, easy procedure, calcination and some sonication is involved. And then we basically compact this metal oxide modified carbon nanotube using a specific dye. Okay, and then we center at high temperature. So what is basically happening here, that at high temperature, the metal oxide particle will be centered or diffused. So it can be used as a welding agent to hold this carbon nanotube together. So we are not adding any binder, and the entire membrane or composite is made of the carbon nanotube. So here the metal oxide will not only work as a binder to hold tightly these carbon nanotube together, but it will also improve the various feature, especially for water treatment, like the surface area. Even it can modify the surface charge. So here this is a schematic or the cross section of the membrane, and we get basically this type of the membrane. So the water can flow through the various spaces between the carbon nanotube and the channel, and here it is held together by these metal oxide or metal. And also we found that these membrane have very attractive feature. It can remove the various heavy metal from water, various organics. Also it exhibited some antibacterial property as well as some anti-fouling characteristic. So we have filed this technology basically, and we have 3 US patent granted to cover various aspects of this technology. And currently we are in negotiation with some water treatment company to see the possibility of commercializing this technology on commercial scale. So then we made basically our own setup, filtration setup. This is designed specifically for this type of the membrane. So we can house this membrane here. And of course, we have everything to measure the pressure difference, the flow rate, and pumping requirement. So it can be used in continuous mode. It can be used in semi-continuous mode. And here the wastewater, around 10-liter tank was used. can be used to remove various pollutant from it in one pass or various passes. So of course you can vary various parameters here to study the performance of these membrane. Okay, I will not go in detail of what we did basically, but I will share that these membrane basically have the potential to remove the pollutant based on size, as well as there are some adsorptive characteristics. So the molecule can be attached to the surface. So this is a unique feature for this membrane. For example, if the surface is negatively charged, which was in our cases, so the cations, for example, cadmium are attached to the surface due to electrostatic interaction. And similarly, there are various sites where molecule are adsorbed on the surface. Some physical adsorption will also occur. So the attractive feature in this membrane is the molecule can be separated based on size, as well as it will be attached to the surface where they can be removed from the water. We also perform some antibacterial study for this membrane, and we use E. coli as a model foulant, and we prepare basically a solution with specific concentration or colony forming unit of the E. coli or bacteria, and we pass those E. coli or those water through the membrane, and we found that membrane with various loading of silver were able to kill bacteria or remove the bacteria from water. Okay, so here these are different membrane with various loading of silver. We found that membrane with 10% of silver were able to kill this huge concentration of the bacteria in just 1 hour. So, which is really a great achievement. And by the way, all the membrane were able to kill the bacteria in 2 hours, but this one shows the most attractive feature. Of course, there are reasons for this. I will not go in detail, but just I want to highlight this. These membrane have excellent antibacterial potential. This is the schematic of the some of the study we did basically. As I mentioned that the carbon nanotube modified with silver, these membrane were able to kill all the bacteria in 1 hour. Similarly, a membrane with 20% silver loading took almost 90 minutes, and 1% silver loading took around 120 minutes. So here you can see that 99% is CNT, okay, and 1% is the silver. So this means that this toxic effect is basically not only coming from the silver. Of course, everyone knows that silver has antibacterial properties, but it also, CNT also has some antibacterial characteristic. So that can be again an attractive feature, and it can be used to treat the water before the desalination or after desalination, even pre-treatment or post-treatment. So if someone is interested to study more in this area, there is another paper. We study basically the anti-fouling characteristic of the iron oxide modified carbon nanotube membrane. So here I want to highlight again that the entire membrane is made of carbon nanotube, and only a smaller loading of the iron oxide were used. So we found that this membrane also have excellent anti-fouling potential. We use sodium alginate as a model foulant. So you can study this paper in detail if you are interested. Again, we found that these membrane have excellent mechanical stability, and we performed diametrical compression test for these membrane. All the membrane have pretty much strength. Again, we found that membrane with 20% iron oxide loading, they have good strength as compared to the other membrane. By the way, in water treatment, mainly this type of strength is not required. Even the smaller strength might be okay. But if you want to apply these membrane for other application, or if it can be exposed in aqueous solution for a longer time, so maybe this type of test will be useful to predict the performance of this membrane. By the way, in diametrical compression test, if the membrane is broken in this direction, it basically show the success of the test. Okay, so what are the few challenges in this area? The manufacturability of these membrane is a challenge because currently we are producing these membrane at lab scale. We can go for the pilot scale and then to commercial scale, so someone can work in this area. The cost of the CNT, although with the time it is decreasing significantly, but still we should search for the method that can produce low cost CNT so that we can apply this in various applications. Then there are some concern about the potential toxic and environmental impacts of the CNT. Although there is no prone study that directly show that its impacts on the human being, but of course it's material on nanoscale, so it should be further explored. If it has some toxic effect, then we should develop some technique to safely use these material. And of course, the application of these material in real water treatment. This is another challenge. All these research at currently is basically on lab scale or the pilot scale. So we should work to bring this into the commercial scale. If anyone is interested to study more about the carbon nanotube membrane, this is one of my review. You can study this. I have highlighted all these techniques in detail. And this is the paper where I highlighted the antibacterial property of the membrane. So you can go and search this paper for more deep insight. Okay, so in the second part of my presentation, I will briefly talk about this novel material Mxenes and why I have selected this. This is specifically for those young researchers, as I mentioned earlier, who are new in this area and they are looking for some topic, especially in water treatment and desalination. So I will briefly talk about this material, its history, its application in water treatment, and the potential research area. So Mxene is basically a new class of the material, 2D transitional metal carbide, nitride, and carbonitride. And why they call it Mxene? Because it is 2D material, and they want to make a resemblance with the graphene, which is also 2D material. And mix it is because it is produced from the mix phase. That's why it is called Mxene. So these are the two guys, Professor Yuri Guguchi, who is the founder of the Mxene, and Michael Najib, who was his PhD student, who developed this Mxene in 2011. So this is comparatively new material, and there is a lot of potential to do some breakthrough research in this area if you are looking for a research topic. So how it is produced, basically, this is a mixed phase. Mixed phase has the general formula of n+1 and what is basically the M is basically the transition metal, okay. A is basically the any element, usually from group 12 to 16, and X denote either carbon and nitrogen, okay, and N represent basically the number of functionalities here. So basically, this is the mixed phase, which has its own application, but we will not discuss in detail. What we do basically, here you have the Al layer, which is the A element basically in this mixed phase. If you remove this A element by some means, okay, then you can form this type of the Mxene, okay. So here the A element or Al is removed. How it can be removed? It can be removed by the etching, which I will talk a little detail in the coming slide, okay. So after removing this Al, this material has some very attractive features, and it has been studied widely in various fields. And again, there is a lot of potential. So I will discuss a little in the coming slides. So the sorry. So the first Mxene was basically produced from the Ti3AlC2. So this is basically the transition metal, and Al is the A element, and carbon was there basically as an X element, okay. So this is basically the elements of the periodic table that can be used for the production of the Mxene. M element, okay, the transition, the surface termination, which are basically OFCl. They are introduced basically after the etching or after the acid treatment, which I will discuss in a while, okay. Until now, we have around 30 Mxene produced commercially, different types of the Mxene, and of course, more than 70 or even 100 are predicted theoretically, okay. So this is, by the way, very new class. It is just developed a few months ago. So till now, N is equal to 4, or 4 layers basically of X is produced. And of course, Mxene where different layers of the X can be produced. I will show you in the coming slide in a little bit detail. So this is how the Mxene can be produced. So you can see here that this is the mix phase, and that contains the transition metal and the carbon, as well as the A layer, which is basically these elements. Okay, this is the M element, this is the A, this is the X, which is the carbon nitrogen, and this is the surface fractionality. So by the selective etching, okay, you can remove basically this aluminum layer or A layer. Okay, it can be another it can be silicon, it can be Si, it can be anything else, but most commonly it is aluminum layer. Okay, so it can be removed, and later on by delamination you can separate these sheets. So if you are able to separate these sheets, you will get some very attractive feature for various applications. Okay, so this is how the Mxene is produced. Basically, the mixed phase can be treated by the HF, and then these aluminum layer or A layer is basically removed, and then after sonication, these different types of sheet can be formed. Okay, you can see here various structures are there based on the number of the carbon layer, transition metal layer, or basically the number of the X layer. Okay. By the way, mixed phase is not only the single precursor to be used for the production of the Mxenes. There are some other non-mixed phases as well. For example, this is one of the Mxene that is produced from the non-mixed phases. So again, there is potential in this area. If you can work and if you can select another mixed phase and you can develop some techniques basically to produce Mxene, so really it will be a breakthrough research in this area, because this is a new field, as I mentioned earlier. This is just or any breakthrough research can make you basically pioneer in this field. Okay, so this is the synthesis method. Basically, I will not go in detail. Of course, I don't have much time. So how can we optimize basically the synthesis condition? Traditionally, the HF or hydrofluoric acid was used basically for etching of the mixed phase. But of course, anyone in this area, they must know that it is very dangerous and very toxic acid. So it's very hard to work in this area. Okay. But if you increase the concentration of the acid, of course, the reaction time will be reduced. With 30%, you will get your etching just in 5 hours. But again, if you use the smaller concentration, you wait longer to get basically the Mxene. Okay. Then you need to basically intercalate, and you need to basically insert some ions in the sheets of the Mxene, and later on some sonication might be required. So different approaches can be used. HF was traditionally used, okay, but there are some issues, environmental issue associated with it. So the latest development is we can use in situ HF techniques, where you are not using HF, but you are using basically LiHF and HCl, and HF will be produced basically inside the solution. Okay, and it will basically etch or remove the aluminum layer. Okay, and later on after sonication, the sheets can be dispersed. So again, there is potential in this area, especially for the chemistry people. And if you can develop some green synthesis techniques to etch or remove this layer, A layer, from the mixed phase, and if you can produce this Mxene by avoiding this HF-free technique, so again, this will be a breakthrough research and any application. So you will be again the pioneer in this field. Okay. What are basically the property of Mxene that make them attractive? It has high surface area. This is especially desired for the water treatment or catalytic application. Hydrophilicity. Okay, ease of functionalization. You can modify the surface of the Mxene easily, and you can tune the surface to make your desired properties. They have active metallic hydroxide, biocompatibility. They have extremely high conductivity. So it can be used for application that require the high electrical conductivity. High transport property, so it can be used for the separation of ions or selective separation of ions. So this is basically the various application of the Mxene and different field, not only environment. Okay, environment is just one area. It has a lot of application in energy, lithium-ion battery, energy storage, catalysis, electronics. Okay, if I talk specifically about environmental application, so it can be used as an adsorbent, as I mentioned for CNT. It can be used in the membrane, and the catalysis, and the sensor. It also has some antibacterial properties. So again, there is a lot of potential in this area, and some study basically showed that these materials have some very attractive features for environmental applications. So if we talk about the removal of the pollutant, okay, so why it will remove the pollutant from water? Because it contains various functional group, and again, you can modify the surface to introduce some more groups. for your desired applications. It has high surface area, which is specifically required for the adsorption. So this means that there are more sites where the molecule can be adsorbed on the surface. It has the adsorptive property, reductive property. It can reduce the molecule from one state to another. For example, it can reduce the chromium 6 to chromium 3. It has some antibacterial characteristic, okay, and the molecule can be trapped into the layers because there are various layers, so it can be trapped basically in various layers between the sheets, so it can be removed. Then if you modify the surface, so of course there will be electrostatic interaction due to ion exchange, okay, in addition to the adsorption. So all these are very attractive features, and most interestingly, you can regenerate these material, so it can be employed in multiple cycle, okay, which is basically the requirement on commercial scale. This is one of the attractive feature. Titanium carbide based Mxene is widely used in water treatment. Again, this is another open area. This is one of the most widely used Mxene in any area. Okay, so someone can work to apply the other Mxene in water treatment and even some other application. And again, as I mentioned, there is a lot of potential to work in this area. So if someone is interested to study in detail, this is one of my latest article on the topic, the environmental application of the Mxene or water treatment application. So you can study in detail, you can find this paper. Mxene also have some desalination potential. Of course, I will not go in detail, but it can be applied in ion saving membrane and capacitor deionization, which I mentioned for the CNT, solar desalination and evaporation desalination. So Mxene can be a wonder material basically in future desalination. Again, if someone is interested, so they can search this article. This is one of my latest article on this topic. I have discussed here the potential of the Mxene and desalination, and you can explore this various application. Okay. This is the final slide. So I will talk mainly the challenges in this area. So this is especially for those guys who see what are basically the opportunity for them to work in this area. So these are some of the challenges. The synthesis route, as I mentioned, you can develop some novel technique with a more focus on green chemistry to avoid the use of this dangerous HF. To produce the Mxene. So there is a lot of potential in this area. The commercial production of the Mxene, all the Mxene produces basically on lab scale or pilot scale. There are 1 or 2 units. So you can work to produce the Mxene on large scale. There are some issues with the aggregation and storage of Mxene, some low temperature below 0 degrees C is required. So you can develop some solution that can you easily store Mxene at normal temperature. Of course, this is new material, so you should explore the toxic effects, environmental as well as the health effects of the Mxene. Mxene has some problem. It can be oxidized easily in the presence of the oxygen. So again, one should focus in this area to develop some method to avoid the oxidation of the Mxene. And as I mentioned, till now, around 30 Mxene structure are developed. So you should work to develop some more structure, even from non-mixed phases or from some other mixed phases. So again, it can be a breakthrough research. And of course, the real environmental application. As I mentioned, all this research is currently based on the lab scale. So one should work in this area to bring this material into the large scale or the commercial or industrial scale. Okay. I will briefly talk about how these material can help actually to combat this pandemic as well. This pandemic, of course, it has affected us globally, but there are some opportunities, especially for those people who are working in environmental research or water treatment research. Okay, so these are some of the opportunity. For example, we should know that whether this coronavirus it is present in water, by the way. We have published some article on this. So it can be transmitted from water or no. Okay, if it is present in water, so what is the way to properly detect and quantify this virus in water. So we need to develop some quantification method and detection method or some sensor. Okay. And if it is transmitted from water to a human, so what are the way to treat the water? We need to explore whether the current water treatment techniques, they are efficient to remove this virus from water or no. So in all these opportunities, these material can play a role. Okay, this material can be used to develop some sensor. They can be used to remove this virus from water. So there is opportunities to employ this material even in the current pandemic situation. Okay, so I will conclude my talk basically that these two material, CNT and Mxene, they have exhibited tremendous potential, and there are various challenges and opportunities, especially in case of Mxene, because as I mentioned, CNT is 30-year-old, Mxene is 10-year-old. So if you explore the new application of this material, or if you develop new structure, so you can do some breakthrough research. Okay. So this is all about my talk today. If you want to discuss more in detail, these are my contact details. So you are welcome to interact with me and to discuss any research collaboration or possible research partnership. And the final, I will briefly say that we have call for papers. We have a special issue in Sustainability Journal, which has impact factor 2.576 for the application of nanomaterial and water treatment. So if someone is interested, you can submit your article. You can even contact me before submission. We are the editor of this special issue. Of course, it has processing charges, but if you have some project or someone can sponsor, so you can submit your paper to this special issue. So this is all about my presentation, and you are most welcome to ask any question if you have.
Thank you so much, sir, for such an informative talk. And water purification is indeed a crucial topic and a need of time. I appreciate the part where you explain the challenges in this field. I assume it will be really helpful for the fresh candidates who have joined us today and who have joined this research direction. The If you have any question, you can raise your hand or just write it down in the chat box. We do have some questions.
Yeah, thank you very much. This is an excellent talk and thoroughly enjoyed that. Sorry, I have a sore throat. Yeah. Yeah, I have a couple of questions, Dr. Hassan. So first question is like, why CNT? Why not other 2D materials? Because as we know, like graphene has almost 2 times of surface area than CNT. So like if we can have some 2D materials which can absorb pollutants in the water as good as CNT, then why not other 2D materials? And the second question is, you talk about AG, like a silver doping on CNT. So silver is perhaps a bit expensive. So how about the other cheap transition metals to be used with CNT? Thank you.
Thank you. Very nice question. Both the questions are very nice. So why CNT basically? Of course, we have worked on graphene as well. And graphene is basically the parent material for the CNT. So of course, graphene has fascinating properties. And we have also worked on some graphene-based membrane as well. But of course, my today talk was the carbon nanotubes. So basically, the carbon nanotubes, it has some feature that are not basically in the graphene. It doesn't mean that graphene is not a good material. Of course, the graphene surface can also be functionalized. But if I talk mainly about water treatment, so if that channel is formed, so that channel can be used for the selective, removal of the pollutant as well as for the flow of water. Okay, so of course there is no direct comparison. We have also worked in graphene, and some researchers are working in graphene. So graphene has basically opened all these doors where I am talking to today. After development of graphene, all these 2D material came into the limelight. So graphene has its own feature. CNT is just we are exploring basically, and we have worked in graphene as well. Inshallah, in future if we have time, so I will share some of my research in graphene-based material membrane as well as adsorbent. Regarding the silver, totally agree with you. Silver is expensive material, but if you see the concentration of silver, so even I have used 1%. So this means that, and my membrane, it is just few gram and even few milligram. So this amount is very smaller. This is one point. And the second point is, of course, we can explore other material. We have just started with the one material, but in this case, we should know that whether this material can be used as a welding agent with the carbon nanotube or no. So in the case of the silver, we have demonstrated that, of course, other material can also be employed. This is just, the beginning. You can play with it, and there is a lot of potential. So yes, it can be employed.
So he thanked you for for answering the question. We have another question from a student. He's asking for some tips on how to grow bacterial culture.
Okay, to be honest, this is not my area. We have our life science, our biology department here, so we have acquired the services of them. They provide us the bacteria in specific concentration, and later on, after treatment, they use the famous technique agar plate method for counting bacteria. So I think someone with the biology background, I think they can answer it more properly.
All right. Another student from Thailand also joined us, and she asked question during the lecture, and now she's not with us, but I want to, ask that question. She asked that is is there a technology to make water purification in terms of dangerous toxins in water? And she said we do molecular separation technology in case of very small toxins. So do we have any specific technology for that?
There are various technology available for the separation of the various pollutant and water, depending upon what type of water you have and what is their concentration. So yes, commercially there are different techniques available, but of course, being a researcher, you are always in quest of improving the existing technology and to play your role and contribute.
Thank you so much. Dr. Tabassum also would like to ask some questions.
Assalamu alaikum, Dr. Ehsan. Thank you so much for a very nice talk. And in fact, your topic was demanding on this Wim Power Pakistan forum. And I also have a couple of questions. So there are many one-dimensional material that have predefined channels. So do you think which materials we can replace by CNTs, because there is a cost issues, stability, yield, time, synthesis, because there are several steps. And for water purification application, we need some smart technique that can be overcome all these issues. So what do you suggest?
Okay, I think I did not hear properly the first part. You are talking about replacing the CNT with other 2D or 1D material, right?
Yeah, because what you explained why you use CNTs because of its channel properties, because they have channel properties and some uniform morphology. There are several other materials that might be quite cheaper than CNTs, and they also have a similar channel and some hollow structure. Then water can easily flow throughout. So what do you think, which material we can replace by CNTs? Because as you mentioned, there are several issues with CNTs: cost, yield, time, and also there is some synthesis issue, because you mentioned there is stepwise. We need some functionalization of CNTs and several in a series steps for synthesis of this kind of membranes. So what do you
Okay.
think? Is there any other quick and smart way to fabricate?
Okay, actually, yeah, there are different material that can be employed. The point here is actually, um, if you see the application and the synthesis of most of the material, some of the challenges are common, especially the cost. Sometimes some material are cheaper than other, but whether you are getting those property or no. So of course, the other material can also be explored. And to be honest, currently I was interacted with some people, and we are thinking. Just I discussed the Mxene. Till now, there is no tubes, or we can say nanotubes of Mxene. And I was discussing with him to see the possibility if we can, produce this Mxene nanotubes. Okay, so of course other material can also be explored. There is no harm. Rather, at the same time, we can work to address these challenges, because these challenges are not the challenges that cannot be overcome. For example, the cost of the CNT every year it is reducing significantly. So if the cost is reduced, you can apply this material. But we should see that the other, I will not specifically mention any specific material, but if the other material has that high specific area, large number of site, if they have the channels, and if they have the compatibility with the most of the material, then of course it can be applied. So of course at research, and we should explore always for the other material, and we can also compare. Of course, being one group in specific area, of course you can work in specific area, but there are many people who are working in different materials. So yeah, it can be replaced.
Okay, thank you so much for explanatory answer. And I have another optimistic question, because as you know, Wimpower Pakistan is dreaming to see the scientific Pakistan for translational research. So I have a similar question to you. Where you see and when your research findings will be transmitted to commercially?
This is an interesting question, and I mentioned in my patent slide that currently we have here one technology transfer office. So currently we are in coordination with one company, and they are working with us if we can bring this technology into commercial scale. So of course, I will say not very soon, because as I mentioned, there are various challenges. Even if I talk about my membrane, so still we are facing some challenges. For example, leaching of the material, not at initial stage, but at larger stage. And then, of course, if it is leach, we should see the toxic effect of the carbon nanotube. Then we are using basically the synthetic water here, which are produced in our lab. We have not tested yet for the commercial water, which have other material. So what will be the matrix effect? So of course it will take time, but yes, we are working in this area. And I think this is one of the prime objective of our research, that it should benefit basically the society. And here I would also highlight that in our country, Pakistan, we should also have these entrepreneurship or technology commercialization offices, where we have in the foreign university, who can work closely with the local industry to solve our indigenous problem, and provide some solution basically. So we are working on that, and we are expecting after some time, after modification, yes, we can have something in the market, inshallah.
Thank you so much, Dr. Ehsan. Similar dreams we have, because recently Karachi is a very big city of Pakistan, and they are facing a lot of problems related with water purification. So definitely we need this is your research is quite interested, and this is a need of time. And I just wish, hope so we will able to translate your research in Pakistan soon. Thank you so much.
Inshallah. Thank you for the nice
Inshallah.
feedback.
Okay, thank you, Dr. Ihsan, for very informative talk about water purification using CNT and Mxenes. My question is like whether the diameter of CNTs and the length of CNTs have any effect on enhancing the performance of the membrane. And my second question is whether these membrane are freestanding or it is adsorption support.
Okay, thank you for the nice question. Yes, the property of CNT affects a lot the characteristic of the membrane. So as I mentioned earlier, that if you have the CNT with smaller diameter, of course, so you will get some more attractive features. And after modification or removal of the catalyst, the length of the CNT is reduced. So we have observed that if the length of the CNT is reduced, so its properties are also disturbed. Or in simple word, if I can say that if the length is reduced, you will be having smaller number of the sites for the adsorption of the molecule. The membrane I described, basically, I'm sure you are talking about the membrane we developed. So yeah, this is basically the novelty in our membrane. They are basically the freestanding. We have not used any support. It is made entirely of the carbon nanotubes. The only welder is basically the metal oxide, which was not used for the purpose of welding only, but to improve the characteristic of the membrane. For example, the surface area of the CNT. So it basically perform a dual function to hold the carbon nanotubes and to improve the characteristic. And that was the main novelty, because the CNT are usually used as a filler. So the polymeric matrix membrane, historically, it was the main matrix, and CNT will be having a loading of 1 to 10%, let's say. But in our case, it is made entirely of the carbon nanotube. We have not added any binder. Instead, we modify with the metal oxide. So it can work as a binder as well as it improve the characteristic. So you can say it's like freestanding.
Okay, that's interesting. Thank you so much for your detailed answer.
Assalamu alaikum. Dr. Ihsan, can you listen me? I'm not sure
Yes.
if I'm okay. Sir, thank you so much for giving us so brief information related to carbon nanotubes for the treatment of water pollution. So after this is a new area for me basically. So I want to ask few questions. My first question is, as you mentioned that you have prepared purely carbon-based nanotubes, I mean no matrix. My question is why? Because if we could add some matrix material like I have worked on silica aerogel. So silica aerogel have large surface area, and for the for water purification, if you could have more surface area for the interaction of pollutant with carbon nanotubes, I think that the properties of carbon nanotubes sheets can be improved. So why not? Because you mentioned that you have just used metal oxide as a welding agent, but is it possible that can we combine carbon nanotubes with some matrix like silica or silica aerogel?
Okay. Thank you. This is a nice question. Actually, why we started this work, traditionally the carbon nanotube was used to improve the characteristic of the existing material. For example, polymeric membrane. People used to add 1% CNT and they found that the property of the membrane was enhanced. And when they increased the loading of the carbon nanotubes, then the property were further enhanced. What we did basically, we thought that if CNT is has some so good characteristic, why not use CNT purely? So if it would possible, we were basically trying to use 100% the carbon nanotube to fully utilize its property. But since it was not possible, so we keep the maximum percentage of the carbon nanotube and smaller percentage of the metal oxide, so that we can utilize fully the properties of the carbon nanotube itself. Reference to the modification of the CNT with other material or its combination, yes, it is possible. For specific application, we need to have some quick checklist. For example, in my case, what I will see, I will basically, if I modify with your material, aerogels, we will see what is its melting temperature, whether it can be used as a centering agent with the CNT or no. But yes, the area is open and there are various material that are used in combination with the carbon nanotube, various polymeric material and various even ceramic. We also work on ceramic membrane where CNT was used as a filler. So yes, there is a potential in this area, but why CNT was used fully? Just to fully utilize or explore its properties.
Right, sir. Thank you so much, sir. I don't have any other question.
All right. Thank you so much, sir, for answering all the questions so generously. If you have any thoughts to share with us, please do share.
Thank you again for providing me this opportunity. It's always interesting to interact with the young researcher, and I really appreciate the efforts of the Women Power Pakistan. So stay strong. My full support with you, and inshallah keep working for the betterment of women in Pakistan and in the field of STEM. So thank you so much.